Hello everyone and welcome back to another LM Math Circle video. Today, in this video, we're going to introduce another new topic that sort of relates to a probability theme. And this topic is going to be expected value. So for some of you, this may be completely brand new. For some of you, you may have heard of it, and some of you, you may know it well. So we're just going to be today doing a brief introduction, just sort of make sure that everyone has a nice understanding of it before we go more in depth, because it has a lot of layers of complexity and difficulty and whatnot. So let's just start off with the basics first, and we'll go from there. So expected value. I guess let's first say, what is expected value? So perhaps an easy explanation would be by taking an example. So let's say that we have a dice, and it has 6 sides, right, 1 through 6. And we're going to try and find the expected value of a single dice roll. So what does that mean? Well, essentially what it means is we're going to check each possibility. So for a dice, we could roll a 1, we could roll a 2, etc. We could roll 6 different numbers. And we're going to see, well, what is the probability of each of those outcomes? So we can make a nice little table. And so the 6 numbers that I've drawn here are 6 possibilities when we roll the dice. So we can call these, we can say this is our x. This is all of our outcomes. X is some outcome. And in this row below it, we're going to find p of x. So what's the probability of each of these outcomes? So what's the probability that we roll a 1? Well, there's 6 sides, and there's only one side that's a 1. So our probability is 1/6. And it's a symmetrical probability, meaning it's going to be the same for all 6 sides. So we have a 1/6 probability for each of these outcomes. So now let's define expected value. Expected value is going to be a formula, and we're going to use capital E of x to denote the expected value of a single dice roll. And so we're going to say sigma, which is a Greek letter, and it just means sum. And in the stomach, we're going to say x times p of x. So in other words, it equals the sum of all of our outcomes times their respective probabilities. So in our case, that's 1 times 1/6 plus 2 times 1/6, because for 1, it has a 1/6 probability. Of rolling a 2, we have a 1/6 probability, and so on. Plus 6 times 1/6. And if we add these all together, we get a number 3.5. So what does this mean? Well, we've realized that our expected value of rolling a dice one time is 3.5. But how does that make sense? Because we know we can't roll a 3.5 physically. We can only roll a 1, a 2, a 3, etc. So what does this number really represent? Essentially, what we can think of it as is if we rolled a dice an infinite amount of times and we averaged our scores for each of those rolls, it would be very, very, very close to 3.5. And we can prove this through some laws and theorems, like the strong law of large numbers, etc. But in general, expected value is the idealized average that reflects the probability of possible outcomes of something. So in our die example, each of the 6 numbers had a probability of 1/6 of being rolled. This means if you roll the die lots and lots of times, you'll see a 1 roughly 1/6 of the time. So etc. If you average all the outcomes of n rolls, eventually you'll see that it's really close to 3.5 as n gets bigger and bigger, meaning as you roll more and more times. So to close out the video, let's do one more short example. So in the top left, you can see that I've written out our formula for expected value. Just to recap one more time, it's the sum of each outcome times its respective probability. So the I that we wrote for the subscript, x sub I, just means for the ith outcome, we're going to multiply it by its probability. And we're going to sum all of those numbers together. So let's do an example. A player tosses 2 coins into the air. He wins $1 for the number of heads he'll get. However, he'll lose $5 if neither coin is a head. So let's calculate the expected value of this game. And let's determine if it's favorable for the player to play this game. So let's just think about what the expected value means. It means if this player plays this game an infinite amount of times, on average, what will his score be? Meaning, if we average all of his scores, how much money is he going to make? And let's decide if it's a favorable game, meaning is he making money from playing this game? So, let's begin by saying, what are our outcomes? So, when we roll 2 coins, we know that we could roll 2 heads. We know we could roll 2 tails. And we know we could roll 1 head and 1 tail. So we have essentially 3 outcomes. And now let's find the probability of each of these outcomes. So first, what's the probability of 2 heads? Well, what's the probability, first, of our first coin flip being a head? 1/2, because it could be heads or it could be tails. And now, on the second coin flip, nothing's going to change. It's still going to be 1/2. So it's going to be 1/2 times 1/2, because we're saying a head and a head. So when we're saying and, we multiply in probability, so that gives us 1/4. And then by symmetry, it'll be the exact same for tails, because we have a 1/2 chance of our first one being a tails, and then for the second one, another 1/2 chance. So it's 1/2 times 1/2, which equals 1/4. And now we can either calculate our third outcome by doing something similar to what we just did, or we can notice that, well, there's only 3 outcomes. Their probabilities have to sum to 1, because that's just simple math, right? We know that one of these outcomes is guaranteed, so the probability of one of these 3 happening is 1. So we can see that, oh, it's 1 minus 1/4 minus 1/4, which equals 1/2. So now we know our probabilities for each of the 3 outcomes. So now let's find our expected value. So for our first outcome, 2 heads, we need to remember that the problem told us that he wins $1 for the number of heads that he gets. So here, if he flips 2 heads, he gets $2. So the value of this outcome is 2. Just like when we rolled a dice, if we rolled a 3, the value was a 3, and we multiplied that by 1/6, because that was the probability of rolling a 3. So here, the probability of 2 heads is 1/4, so we multiply that, and then we add. So for our second term, it says he loses $5 if neither coin is a head. So here's going to lose $5. So his value is -5, right? We multiply that by the probability of 2 tails, 1/4. And finally, we'll add the third outcome, which is 1 head and 1 tail. So he's not going to lose any money because he did flip 1 head. And that means that he's going to get $1 for that 1 head that he flipped. So the value is 1. And we multiply it by the probability of this outcome, which is 1/2. And now we can add these 3 terms together. So we see it's 1/2 minus 5/4 plus 1/2. So we see that simplifies to 1 minus 5 over 4, which simplifies to negative 1/4. So just like the dice roll example, none of the outcomes produce a value of negative 1/4. But if this guy plays this game an infinite amount of times, and even not even an infinite, but a super big number, and he averages out his score, it's going to become negative 1/4. So to answer the second question, it was, is this game favorable? No, because on average, over a long period of time, he's going to lose 25 cents or a quarter of a dollar. So this guy should not play this game. And he knows this because of our handy expected value theorem. So it's a cool sort of insight into how we can begin to use math in real world problems. Of course, it's a very simple example, but as you learn more complex math and more complex applications of expected value, it becomes super interesting. So I hope you guys enjoyed the video and you learned something. And as always, any questions, don't hesitate to reach out to ask us. And of course, you can bring those questions to the Zoom meeting. And I hope that we see a lot of you there, and that I hope you guys try the problem set. And thank you for watching. Bye. I'm not going to lose any money.